Gardner, or Paul Gardner's friends were feeling left out. So if anyone sees Paul, I think the name's Gardner, or Paul Gallagher, excuse me. We want to wish Paul Gallagher a very happy birthday. Is Paul here? He's outside. Okay, fine. We'll wish Paul a happy birthday in a few minutes. So there's dessert available outside. This is a reminder that the network really and truly is going down at 4 o'clock sharp. So download your email, surf your web pages, whatever. We're tearing down the network promptly. Also, if you do have wireless cards, please return them. The folks in the back, Sarah's waving her hands, and I think John's back there? Yes. If you have them, please return them. And we might even have a few available still for, do we? I'm getting a haphazard, yeah. Yeah. Okay, so there's a few even available for loan if folks haven't tried the technology yet. Also, I had a couple of questions during the break of how does one get to talk at NANOG? Well, send mail to NANOG support, and generally we send the mail out to a number of other folks to look it over and see if the abstract would be of interest. So that's how you get to speak at NANOG. Just want to reiterate while we're waiting for, oh, it's okay now? Just wanted to reiterate a few points about the NANOG mailing list. And really sorry, are you laughing at me? If you have something to say, just say it. We have, so I really want to make this big push that, again, the NANOG email volume is just growing way out of bounds. So there's been a number of suggestions about what we might be able to do about the mailing list. And what we've tried doing is sending out gentle reminders now and then, some of the NANOG staff saying, you know, this really isn't on topic, or you probably shouldn't use those words in public email, or things of that nature. And there's some success to that. The other thing that seems to work is public ridicule. And I think we've got Randy Bush and Jayhawk and others to thank for this. But it also is a lot of email volume, and generally, you know, public ridicule also is not operational email. So what I would actually prefer is private ridicule. If you do think someone's topic is way out of bounds, send it to them privately. Vent your anger, your frustrations, whatever. The 5,000 or 6,000 people on the NANOG list really don't need to see that. So private ridicule. If you do feel the need to ridicule, private is preferred over public. So sometimes public is more successful. It's also been suggested that we kind of randomly drop or base a filtering based on the originator, do some type of random early discard. But we're a little hesitant to start actually. We're a big believer that the mailing list should be an open forum for discussion of ideas and operational topics. So we're a little hesitant to actually begin any type of heavy-handed moderation. There's also been a number of discussions about maybe setting up a group of 10 or 8 or 6 moderators, any one of whom could approve a message, so the burden would be shifted over a number of people, and there would not be one NANOG czar. But we're also a little reluctant to do that. There's a few technical issues, and we really rather not go the moderation route. I think our preference is restraint. That is, you know, I know you really want to send that mail out, but really think that does everyone on the mailing list really need to see that email? And again, okay, with that, we'll now have our first afternoon talk with Cathy speaking about car. I'm sorry? Oh, Paul? Where are you, Paul? Paul Gallagher? Paul? Would you please stand up, Paul? Paul, some of you... Paul, we don't have time to sing you happy birthday. We don't have any cake for you, but your friends were feeling left out. And collectively, we'd all like to wish you happy birthday. So, happy birthday, Paul. What would you like to do? Oh, are you using mine here?
I'm using my laptop.
Okay.
Because I was told I had to.
Yeah. Your laptop is live.
Is it? Okay.
Can
you hear me? Hello? What? Oh, there it is. So, hi, I'm Cathy Wittbrodt. I work for At Home, the evil cable empire. And, as Ed says, and I'm going to talk a little bit about some interesting happenings that we had when we were trying to configure this Cisco proprietary feature called CAR. And there seemed to be a lot of interest, so I thought I'd present it here. And the question of the day is whether he's afraid of the car, excited about the car, or the car is going to run him over. And you can decide that for yourself. So, oh, did I go the wrong way? Oh, no. Okay, so first of all, I'm going to talk about what CAR is, what we did to test in the lab, the rate limit parameters that we use and how we set them, the different tests that we did. This is just pretty much an overview. So, and some performance issues. There are lots of those. So what is CAR? It's a token bucket mechanism, and I'll talk about that a little bit more in a minute, that does a number of things. It does packet classification, so you can set toss bits in the packet header, and it also does, for some definition of rate limiting, it does rate limiting. It's configured on a per interface basis, in or out. It's a rate limit that the rate limit, most of the testing we did was the rate limiting testing because we had some managers who felt that we could use this in interesting ways in our network. So the rate limits are based on extended access lists, all the standard things. You can also set toss bits somewhere else and then rate limit based on those, or classify them again based on those. So you can color traffic. I'm talking ahead of myself. There's this URL. You can actually search for it on their webpage if you want to read the marketing stuff, but I don't have any of that because I don't work there. So more about CAR. The rate limits are defined. There's several parameters, and when we started to configure this, we asked Cisco, how do you configure this? And they said, oh, well, you configure it. And we said, no, really, how do you configure it? And they said, no, you just configure it. And so we decided that instead of guessing, we would go in the lab and figure out how to configure it. So there's several parameters. There's the rate that you want to have in the rate limiting stuff. There's the rate that you want to have on the average over a particular interface, and based on whatever classifications you put on that interface. And then there's these config parameters, the normal burst and extended burst, and I'll talk a lot about those in a minute. And then based on those, you can make decisions about whether to set precedents, to drop packets, to transmit packets, and all those sorts of things. Or you can drop it into another rate queue if you're so inclined. And you can have a bunch of rate limits per interface, but as you'll see, the more you have, the more interesting it gets. So what CAR isn't is a traffic shaping mechanism. So if you expect that between the two routers that are running this, that that TCP speakers are going to think that the link is actually whatever rate limit you set, you're wrong. It lets you burst and then drops packets, but we'll talk about that some more. It's not what I would call QoS, but then it's also not a performance enhancement for your routers. But we'll talk about that some more too. And a couple additional bullets. It's not a solution for the address-based conspiracy, and it won't stop postal mail spam. So let's talk a little bit about how a token bucket works, because it's actually really relevant to what we found in our testing. I consulted the king of clip art, and so I have some whimsical clip art. So in the configuration parameters, the bit per second rate that you set on your rate limit is basically how fast the tokens are falling into the bucket, okay? So those little red dots. And then the normal burst parameter is how high the bucket is. And the way this works is if the packets are going by and there's enough tokens that represent the size of that packet, then the packet passes or conforms. Whatever your conform, you can transmit, you can set precedents, you can do a number of things. And if there aren't tokens, then it does whatever your exceed is, drops or sets precedents or puts it in another rate queue. And there's also another parameter that I'll talk a lot about, which is the extended bucket, which lets you kind of steal tokens in interesting ways. Does anybody have any? If you have questions, feel free to ask. So how is it configured? It's a regular old interface, Cisco configuration command with the normal burst, extended burst, exceed action. So, like I said with the token bucket in this configuration, the normal burst is what conforms, and the extended burst is how to steal tokens. This is what our topology looked like in the lab. We had two VSDI boxes running TTCP and TCP trace. And actually, we first did just, testing to see if it would make our routers roll over. And then we did a test in a market that we didn't have any paying customers in. And then we went back into the lab and said, gee, we better be more scientific about this because there's a lot of things happening that we didn't understand. So what we did was the rate limit, I have this great laser pointer, was placed here, and we were sending traffic across this. And this is a 10 megabit interface that was rate limited to 128K for this test. But actually the rate limit the behavior was the same regardless of what the rate limit was, and I'll show you why. So the first test we did was we just wanted to look at the height of the bucket. We didn't want to look at, borrowing tokens. So if you set the normal burst and the extended burst to be the same, then there is no extended bucket. Okay, so that's what we did in these tests. And we did multiple tests of sending traffic across that interface at each one of these points on the graph, and there are three different things going on here. The top line, the red line, is really your throughput. And then the magenta line is the number of retransmits, and the bottom line is the number of exceed packets. So we were actually looking at, there's a car MIB, and we were actually looking at, what actually, there were no tokens, so, it exceeded, and so then it got dropped. And what you can see from this is that when you get to about 2400K for the bucket height, it really levels out. And we actually figured after long occurrence of events, figured out why that is. But if you also look, if you don't use the extended bucket at all, you end up with about 20% retransmits. And depending on where you put this in your infrastructure, that means that, over time you're getting 128K or whatever, but you're sending a lot more packets than. So if you're using it to conserve bandwidth, you should be really careful where you're putting it. So this is a TCP trace, and the only point of this is that the slope of the line, even though, as we'll zoom in, there's some interesting things happening. The slope of the line really is whatever your rate limit is. And as you zoom in, what you see is that, you start sending, and this is pretty much all TCP traffic because UDP doesn't have this characteristic. And then TCP will back off because you dropped packets, right? You sucked all the tokens out of the bucket. You drop the packet, TCP backs off for a second and a half. That's how long that flat line is. You get the retransmits back. You start opening the window again. You drop a packet, and it just keeps happening over and over. So, and this is just a little bit closer, so you can see the little packets and the little retransmits. And we did a couple other tests along the way that are interesting, comparing car to traffic shaping, which remember we said car wasn't traffic shaping. And if you look at, we did the same test, although we didn't zoom in. We did the same test with, we traffic shaped a PVC across that test lab, and we did a similar test. And of course, it traffic shapes. It doesn't drop it doesn't rate limit by dropping packets. It just slows things down so that the equipment thinks that it's a slower link, and it behaves a lot better. We also did some generic traffic shaping tests. Cisco has this feature, generic traffic shaping, although it doesn't have as many knobs and it's slow switched, but some of the new stuff that they may be doing uses this, so we wanted to make sure it behaves, and it seemed to behave. So the next thing that we did was we started looking at the extended bucket, and there's a lot of gory details here. We said, gee, how does the extended bucket work? And they said, can we get back to you? So we started testing with it, and actually, these are going to be up on the web, so there's a lot more detail to this, but basically it's a way to steal tokens, and you have this thing called compounded debt, and instead of running out of tokens and dropping all the packets, you drop one based on this. You borrow some, and then it's more like, they say it's more like red, but we weren't really convinced of that. But anyway, it does behave quite a bit better. So what we did was we left the normal burst at 24K because that's what levels out. And then we started messing with the extended burst. And what we found, this is a similar graph as before, as you go out in the increments of modifying the extended burst, you can get the retransmits down to about 7%, which is, a little bit more well-behaved, and the retransmits and the exceed packets coincide. You don't end up with more retransmits than exceed packets, which is probably a good thing. What we found was that the extended bucket should be twice the normal bucket. And we thought a lot about why that is, and what you set the height of the bucket at. And as it turns out, I hope it's the next slide. Oh, these are some zoom-ins like before. You can see the little retransmits. There are less of them. I guess I won't give you the punchline now. We'll talk about multiple streams. Sorry. So then we did some tests. We did a couple tests that I don't have slides on. We did a test injecting delay, and the results were really similar. We also did multiple streams because one of the things, for better or for worse, that people were talking about doing with this is there was a misconception among some of my coworkers that the way this worked is that every individual flow got a certain amount of bandwidth, but really it's like a bulk thing, right? So if you're the only guy talking and you don't suck up all the tokens, then you're not even going to notice. So what we did was we took one stream at 128, two at twice that, and three at 3 times that, and found that they kind of sync up and drop at the same time over time, and they each get about 1/3, with 3 of them 1/3 of whatever your rate limit is, and the packet loss is really the retransmits are pretty much the same. So it's consistent. It seems consistent with multiple flows. So what we discovered was that the height of the bucket is how many tokens can fill it up in a second and a half, because that's how long TCP takes to back off, and that's why it's 2400K with a 128K rate limit. And the extended bucket is twice that. So we came up with this little formula that I guess Cisco gives out to their customers now. It made it all the way to Belgium. So let's see. So what did we do? So then what we did was we put some of this in the field, except that instead of dropping packets, we transmitted for the exceed action and the conform action, we transmitted instead of dropping, just to see kind of what the effects on the equipment would be. And we put tools in place to watch like VIP CPU utilization, exceed counters, all those sorts of things. And we used Cisco 7500s, no big surprise. They were really busy routers, which is interesting. We had different kinds of VIPs. I'll talk about that in a minute. And we used 5 different rate classes. You kind of have to, depending on what you're doing, because you have to make sure that the stuff that you don't want, if it's in a block of address space that you're affecting by the next rate limit, order is important, so you have to play these games with these rate limits that you never intended to have. So what did we find? As the filter length and the number of queues got bigger, the performance got more interesting. The more queues, like I said, the more queues you have, the more interesting the router behaves. VIP 250 seemed better. Let's see. We started seeing, I'll show you some graphs that are pretty interesting of this really, high VIP CPU. Who watches VIP CPU utilization? Has anybody gotten any useful information out of Cisco about what it means? Has anybody seen the graph? Well, apparently 100% VIP CPU utilization doesn't necessarily mean that your router is going to die. And we're not really sure what it means, so if anybody has any input to that, it'd be really interesting. And if you have more traffic going in one interface than out the other, then it does this queuing on the VIP, which makes the CPU go up. And if you're at 100%, if you send more traffic, it's supposed to get better. But I don't quite understand that. But I guess it's more that you can do in an interrupt, then the better it performs. And like I said, depending on where you put it in the infrastructure, you could be generating a lot more traffic than you think you are. Here are a couple graphs of some VIP CPU utilization that actually we see with car turned off. that we've been trying to figure out, and the top line is 100%. So I don't know who watches it, but I'd be interested in talking to folks about what they see and what they think it means. So one thing that we do use this for, I don't think we're going to use it for what we originally intended to use it for, but one of the things we found really useful is we rate limit ICMP at the interconnect, and we plot the exceeds, and we have alarms in the NOC that say, you know, the rate limit's being exceeded, and we watch all the attacks, but they get dropped at the edge. It's very cool. And we can see, you know, how much, and track them down but it's not melting down the middle of our infrastructure, which is pretty useful. And you don't need any of this formula for that because it's ICMP, and who cares how many you drop. And I would suggest using it maybe for customer ingress filtering, but I wouldn't use it for, you know, the balance of our traffic is from the internet in a lot of cases. So it doesn't do you a whole lot of good to rate limit what goes out because they're sucking down a lot more than they're sending. Some of the new cable modem gear uses CAR from a particular vendor that we know, and we're trying to get that fixed. So anyway, that's what I had to say. So, any questions? Uh-oh.
Oh, shock. I have two questions, both theoretical, unfortunately. First is multi-parse. Were somebody to give you a tool whereby you could impose a traditional leaky bucket in front of your association or your collection of token buckets so that you could actually smooth out the traffic and have it behave as if it was an interface of bandwidth X, would this be very useful for you?
If it had at least as good or not better knobs than, and, you know, but yeah, I mean, I don't know whether we would want to buy an external box or not. It depends. Because
well, I imagine that your vendor would do this, whoever your vendor happens to be.
Right. I mean, traffic shaping is for what we were doing, traffic shaping was what we were looking for, and this is not that.
Right. So you are looking for traffic shaping as well, which is
right.
Interesting. This is simple. Take notes, Paul. How long a queue would you expect to have in front of the traffic shaping leaky bucket? And what kind of queue management would you use, like red or maybe something else along those lines? Do you have any thoughts on that?
I haven't really thought about it. Probably red, and I don't really. I mean, we'd have to look more. Some of this has been sort of an adventure in looking at all of our different kinds of traffic and trying to figure out, you know, what makes sense. And I'm not really sure if I can speak to that yet.
Okay, that's fair, because we were running through the same things.
Yeah.
The other question is, suppose somebody were to give you another control plane where rather than a set or hierarchical or rule-based collection of token buckets where you can have a certain class of traffic interact with bucket X, certain class of traffic interact with bucket Y, and so forth, you get a further fine-grained interaction with each individual token bucket where you can weight any given traffic
that would be
with
great.
A certain number of tokens.
That would be great.
Yeah? Okay.
Yeah.
So basically, neat technology needs more knobs.
Right. I mean, you know, it's not real. It doesn't take a whole lot to think of different ways to use this. I mean, listening to the caching talk, right? I mean, you want to incent people to use the cache. Well, how do you do that? You make the traffic that doesn't go through certain kinds of traffic that should be cached worse if they don't go through the cache. You know, stuff like that. So, well, you know, it's not my idea, okay? You know. But you know, I mean. Come on, we've all thought about it, you know. I mean, that cache is the 30% performance hit. You better make it worth their while, right? So
just on exactly that note, to summarize, maybe there are a couple providers who think that a stupid FIFO-based network is not optimal, and that having better tools to shape and manage traffic is a good thing.
Because it's not shaping traffic; it's facilitating other traffic flows. That's what the marketing people told me, and I believe it.
Okay.
And you know, that's what it's all about, right?
Vendors, both the C vendor and other potential vendors, take note.
I did want to make a comment about where it is useful to put this in, and one of the places that we found it useful was at the customer ingress.
Absolutely.
Specifically to drop traffic that's not going to be returned.
Oh, that's a good idea, sure.
Right.
Right, you can match it, drop it all. Yep, absolutely.
Yep. And that if you've got asymmetric traffic flows, and this could be at a data center or it could be at a customer ingress point, where you're getting a lot of requests in, but then you're choking with the responses back. You can rate limit just the inbound requests to tune it so that your outbound responses don't congest, but you're whacking off the requests as far outside of your network as you can.
Right, and
You can also save your servers that way, because they're not processing as many requests and not having to retransmit their response traffic.
right. The thing you have to watch when you do that, though, is if you're rate limiting the requests, you want to put that as close to the outside as you can, and putting that on a busy interconnect router is not an optimum thing to do. Trust me.
Oh. Yeah, it's definitely best to put it at the thin periphery,
Right.
at the customer.
But if you
entry.
put it at the customer and it's inbound, then you take the hit of all the retransmits.
Yep.
So,
But the issue then is also, if you've got a very broad periphery accessing the center of your network, you can't identify all the requests into the center of your network and coordinate the rate limiting all the way across your periphery.
right.
So it does make sense to put it in strategic places in the core of your network to guard your servers.
And it's also a fine thing to think about when you're addressing your servers, that you might want to do something like this. And, we got one of our vendors to make it so that we have these, this block of sort of floated address space that's, one line and a filter, so that, when requests go outside our network from these servers, the source address is one of those well-known addresses. We didn't give them all the same address, though. Anyway, so that we could put it as one line in the rate limit, because otherwise you end up with 200 lines and then you're kind of hosed. Huh?
Cathy, real quickly, one thing in your slide that said, what car isn't.
Mm-hmm.
I was waiting for a slide to come along which didn't, which perhaps you can make a comment about now, is that car is not a dropper either. So maybe you could say a couple words on the relationship between car and, weighted red?
I'm not sure if I know what you're getting at. I mean, car is certainly marketed as a traffic shaper, even though it's not. Okay, by Cisco. I mean, I have white papers all over the place, they say. So, I mean,
That's been a lot of time as a banking product manager.
certainly if you had a congested link and you wanted to do something smart with it, then sure, you would want to use red or something. But the goal of some of the stuff we're doing isn't necessarily to uncongest a congested link, if that's what you're saying. It's to modify subscriber behavior and differentiate services. And so it isn't necessarily that we have some sort of saturated link that we're trying to... So that's, I think Sean and I are both on the same page with the sort of knobs we'd like to see, because we're not doing something like, dealing with a transatlantic congested link or something. So yeah, there is a big difference between this and a real congestion mechanism.
Yeah, I was wondering if you could elaborate on your lab results on the performance degradation on the 7513 or the 7500 series on the router. You mentioned that it's almost like a two-part question. The health of the VIP processor versus the overall processor of the router, what kind of performance degradation on each side, and how the VIP interacts with that, and how it can help control the car. The second part of the question would be, what other kind of car circuits, did you just have one coming in with one set of access list applying or queues applying to that circuit, or were there multiple circuits coming in with other types of links going out? As basically the second part of the question, as your amount of car circuits grow, how much more of a degradation on the overall router would you be seeing? I don't know if your lab results...
Well, we could certainly speculate on some of that. Let's see, where to start? That was big. The VIP does most of the processing. We didn't see a lot of impact on the RSP CPU, if that's what you're asking. I mean, most of the processing that we could tell is done on the VIP. If the traffic coming in, I mean, we had it coming in the field when we were doing transit, we had it coming in on a really busy router. Input on a really busy interface, output on a bunch of different slower interfaces. And if all that traffic, if there's plenty of out for what's coming in, then it behaves better because it's not queuing up all the stuff that should be going out. And that's just without car. That's just in general. So if you have plenty of egress, then it behaves better. It seems that the VIPs that had more than one interface, that had a little bit more traffic, I guess because of the economies of scale of what you can do in an interrupt, it seemed to behave a little bit better. We're still sort of trying to correlate. Actually, one of the things I'm hoping to do is have a little bit more, information about correlating VIP CPU with what's really going on in the router and getting Cisco to help. But it's been really, speculative at best. So I don't know if that answered your question. It was long, and I have no memory. So.
Yeah, that addressed the first part of the question. I guess the second part of the question was addressing the amount of car circuits you have coming in, ingress and egress, versus just regular circuits applied to the box that you might not have car applied to. Was it a mixture of circuits, or were you just strictly looking at cars?
We were turning it on particular interfaces. The busy routers, we only had it on one interface. And then there were a whole bunch of other interfaces. And some of the VIPs that we had it turned on had another interface on that same VIP that wasn't running car. But I can't say that we turned it on more than one interface in a box. But I would suspect that if they're on separate VIPs, it wouldn't matter because the VIPs have their own processor. And so as long as you didn't have, I don't know, two interfaces on the same VIP running car, that could be bad. I don't think I'd recommend that. But so, we only had it on one interface at a time. So.
CPU-wise, nobody understands how the distributed output buffering on the input cards does things, so nobody will be able to answer you. I just want to actually make a comment and amplify your point to Paul in particular, because he was the one who raised the question. The deficiency of CAR is that it seems like a really popular use of CAR is to make it look as if there is less bandwidth available than the line rate is. Some people use it at an exchange point where you have a broadcast network, or where you have a situation where you have a customer who comes in with a particular fixed length line rate and is unable to do DSU to DSU subrates, for example, and you want to constrain the traffic to some smaller megabit per second rate than is available on the link. The problem with CAR is that there's absolutely no buffering to speak of in front of the token bucket. So there's no timer-based reaction on the part of congestion-avoiding traffic like TCP. Basically, the only way that TCPs can adapt is to see the brute force dropping of lots of packets. And unfortunately, there's no way to drop packets more intelligently than, not conforming toss away. And some work on introducing a queue, whether before or after the token bucket as an admission mechanism, would be really very useful for that kind of application, which is certainly what we're doing, and I think to some extent what Cathy is doing as well.
One more question.
Hi, Cathy. Did I hear you right in the sense that you're using this thing to ameliorate the impact of Smurf attacks on your customers?
Absolutely, yeah. It's been really, because see, we have all these people with really fast connections in their homes with kids that make people mad in chat rooms. So, well, it's true. It happens all the time. So we get attacked a lot, and so we do have a rate limit on each one of the our NAP routers inbound that rate limits ICMP. We have to watch the exceed counter so that the NOC knows when when we're being attacked, so that they know that the customer's complaining because they can't ping their favorite website. It's because we're rate limiting, not necessarily because their web traffic is any slower. So there's a lot of operational issues. But there is a MIB, and it's really easy to make an alert show up in your NOC. But yeah, we do, and it's been really helpful. It saved us, we get, 30 megs of ICMP traffic for, 2 hours every 15 minutes. It's huge. Looking at the plots was just amazing. How much, even little ones that we didn't even know were going on. So now we get the alerts, we can try to track them down. It's been really useful.